Hey everybody, my name is Sean and welcome to our September lecture series. So this lecture, we're going to be going through a lot of exam revision because this is the time of year where it's all just crunch, crunch, crunch and lots of exam revision. So hopefully by this time you've started some exam revision, if not for physics, hopefully for your other subjects. If not, that is perfectly okay. This lecture will help you go through a lot of the basics, help you give you a refresher of all these topics that you may have forgotten about. If you already started some exam revision, first of all, good on you. Hopefully this lecture gives you a bit of an idea of what to expect and a lot of the types of questions and a lot of mistakes that students make. So hopefully you don't make those mistakes. So just quickly, this lecture is brought to you by 8R Notes, and what we do here, we provide students with lots of paid and free resources, such as these lectures. These revision lectures are something that we've been running consistently for about 10 or so years. About 10 or so years. So we also have a bunch of other resources such as study notes, revision guides, flashcards, exam papers, and if you're interested in any of those, head over to the 8R Notes website and hopefully you can find what you are looking for. So with that out of the way, what are we going to be doing today? So the plan for today is going to be second. Cool. Let me just get my pen. Sweet. So the plan for today is we're going to be doing as many VCA questions as we possibly can, and we really want to be focusing on the harder questions, so we know what to expect and we can see where students are making a lot of mistakes. What I'm not going to be doing is going through whole content summaries because by this time it's expected that you know a lot of the content. If you don't, I highly recommend that you go through your notes, go through your textbook, and just quickly just revise what you've done, revise your notes, and hopefully that gives you a better understanding of the topics. That being said, I'm going to be going through a lot of questions, so if you feel like it's going too fast, feel free to pause or just take a quick screenshot so you can finish those questions in your own time later on. Cool, so with second. Cool. With all that out of the way, I will get started with just quickly how you would answer exam questions. So when it comes to the calculation questions are usually around 2 marks. 2 marks, you get 1 mark for correct substitution, and you get 1 mark for obviously getting the answer correct with the correct units if necessary. What you do not get marks for is writing down the formula. The reason for this is because anyone can just write down a formula and you don't actually get marks for those. But that being said, even though you don't get marks for writing the formula itself, I would still recommend that you write the formula down. The reason being is because even though you don't get marks, what it helps you streamline your thinking process when it comes to exam pressure. And if you write down the formula, it helps you, one, substitute your values correctly, and two, it helps you rearrange the formula, especially when it comes to some harder calculation questions. So just quickly, calculation questions, 1 mark for 1 mark for substitution, 1 mark for final answer. Some of the harder 3 mark questions, they usually require, so if you ever see a question with 3 marks, that tells you that there's at least 2 or 3 steps. Usually it involves 2 steps of calculation, and obviously 2 steps of calculation, which are 2 marks, and 1 mark obviously for your final answer. The second type of question that we can get are worded theory questions. Thing with worded theory questions is that physics teachers are pretty lazy. They don't like reading paragraphs of text. And again, this is not a physics, not an English exam, and we don't expect full paragraphs of answers. So dot points are more than sufficient. Cool. And when you're answering with dot points, there's a few things that you want to keep in mind. So first of all, you want to start off with the overarching theory of the question. So for example, let's say you are answering a question about EMF. You want to explain just briefly the overarching theory of EMF. So you're talking about the change in flux, change in magnetic field, or anything along those lines. If you can include a formula, that is amazing. And if you can, you should be definitely be including some sort of formula. Once that's done, you can use the theory that you just explained from the previous dot point and explain it in terms of the context of the question. And finally, you want to be linking back to the actual question, some sort of final statement. What usually happens is when it comes to theory questions, especially when it comes to um, Unit 4, when you get asked theory questions with light and matter, a lot of students have what I like to call pre-written answers, and that's completely fine. But the issue with those pre-written answers is that students don't link back to the original question. And so you can have the most perfect pre-written answer. If it doesn't link back to the questions, you are not going to get any marks for that. So this example below is a pretty good example of how you can formulate your written answers. So this question, explain why the normal force and the weight force are not an example of Newton's third law. So first of all, what the answer has done, they've explained what Newton's third law is. If you don't know what Newton's third law is, this is good cheat sheet material. You just put all of Newton's laws in there. Yeah, it's better to have it on your cheat sheet than to rely on your memory. So yeah, this question explains Newton's third law. Explains how the force of A on B is equal to the force of B on A. And second dot point, it's explaining where this weight force is coming from. It's coming from the gravitational attraction, whereas the normal force is coming from the Earth's surface pushing up on the object. And because these things are different, it cannot be an example of Newton's third law. And this is kind of like our concluding statement, which links back to the original question about why the normal force and the wave force are not the same. I want you to keep this answer in the back of your mind because we're going to come back to this in a similar question. Cool. So next up, projectile motion. This is something you would have done in term 1. I know it's been a while, you might have forgotten how these things work, but the essence of projectile motion is this. So as long as you can keep in mind that the horizontal velocity and the vertical velocities are independent, meaning they do not relate with one another, you should be pretty fine with these. So when it comes to the horizontal velocity is always constant. So you can use this formula where velocity is just distance over time, or distance is velocity times time. Because the horizontal velocity is not changing, you can just use these formulas as is. When it comes to the vertical velocity, there is an acceleration, which is 9.8 or 9.81 meters per second downwards. And because of this, the only force that is acting on a projectile is the gravitational force, which is pushing it downwards. There's another dot point here where it says excluding air resistance. You will never be asked to calculate a projectile motion with air resistance. That is just way beyond VCE physics. What you do need to know is what we call the qualitative effects of air resistance. So the question usually goes like, if there was air resistance, how would this impact a projectile motion? So if there is air resistance, we know that the object will slow down, and it will either slow down or it won't go as high. It won't go as high. And as long as you touch on those two things, you should be fine with the qualitative effects of air resistance. Another trick question when it comes to projectile motion is the difference between get my mouse. The difference between speed and velocity. The thing with this is you have to keep in mind that speed and velocity are not the same thing. So some questions you'll be asked to calculate what will be the speed of the projectile when the projectile finishes its trajectory. So when you're asked to calculate speed, we know speed is a scalar constant, a scalar value, whereas velocity has a magnitude and a direction. So if you're ever asked to calculate the speed, it wants the scalar. What is the scalar amount of how fast the object is going? So the way you would do this is you have to draw a right angle triangle. And because the horizontal and the vertical velocities are independent, we can graph these two on the triangle. So we know the velocity in the x is going to be here, velocity in the y is going to be here. When it's asking for the speed of a projectile, it is asking what is the hypotenuse of this triangle. And the speed is going to be in meters per second, and it's not going to have a direction. And yeah, so the way you calculate speed is you use your Pythagorean theorem, and there'll be velocity in the x, velocity in the y, the velocity x squared plus the velocity y squared, square rooted will give you your speed, which again is scalar, and it is not the same as the velocity. So that is something that you have to keep in mind. Cool. Newton's third law, we briefly touched on it before. Newton's third law, pretty straightforward. Newton's second law says that F equals ma, or if you act with a non-zero net force on an object, that object will accelerating. And that object will keep accelerating unless it's acted upon by an external force. And third law is just equal and opposite forces. So these things are really good cheat sheet material. When it comes to your cheat sheet, I highly recommend that you put a lot of theory stuff, like things like these, things like definitions. So if you want to include definitions of like non-zero or at rest, things like this. These are good cheat sheet things that should be going on your cheat sheet. If something is at rest or is traveling at a constant velocity, this means the net force is equal to 0. So just keep in mind, if it's at rest or if it's a constant velocity, it doesn't matter how fast an object's traveling, as long as the speed is constant, the net force acting on the object will be 0. And the third law, equal and opposite forces. We'll do a quick question. This question 9 from, I think, 2022 VCE exam. So in this question, each student is pulling with a magnitude of 400 newtons. So if you were to draw the force diagrams, it will look something like this. So this student is pulling this way with 400 newtons, and this other student is pulling in this direction with 400 newtons. Cool. And the question is asking, what is the magnitude of force on the student by the rope? And so we know there's 400 newtons on the rope by the student. So if we are applying Newton's third law, on each one of these students, they're going to experience 400 newtons of force in the other direction. Cool. Hopefully that makes sense. If you have any questions, if you guys are watching this live, if you have any questions, put them in the chat below, and either me or someone else will answer those questions as soon as possible. It can be questions about whatever we're doing, or just physics, physics, exam revision, just anything in general. Cool. This brings us to this question. I believe it's question 4 of the 2021 exam. Just write that down. 2021 exam. This question is probably the most notorious question in the entirety of physics. So I'll let you quickly just read this question. So this question, we have some person, Lisa, um, and we've been told that she's applying 500 newtons of force, 500 newtons of gravitational force downwards. What we want to find is what is the reaction force in this scenario. Cool. So this is 500 newtons downwards of gravitational force. I'll show you what a lot of students did. So 500 newtons of gravity downwards. So obviously the reaction force is going to be 500 newtons upwards, 100 newton upwards, and this is going to be the reaction force. Let's spell reaction force of the Earth on Lisa. And unfortunately, that is what that is what about 92% of students wrote, and all of those 92% of students got that question completely wrong. Cool, and the reason this is wrong, it's not very intuitive, but the reason this is wrong. So this question is obviously to do with Newton's third law. So we know Newton's third law is equal in magnitude. We know it's equal magnitude. We know it's opposite direction. Opposite direction. So obviously the reaction force is going to be 500 newtons in the opposite direction. However, there is one thing that you have to keep in mind when it comes to action-reaction forces, and that is that action-reaction forces are of the same type of force. And this is the key point that about 92% of students completely missed. And so because we're saying it's the same type, Lisa is currently exerting Lisa is currently exerting 500 newtons of gravitational force on the ground. So the reaction force is going to be 500 newtons in the opposite direction, but it's not going to be the normal force, it's going to be gravitational force. And so if it's the gravitational force, the reaction force is then 500 newtons, 500 newtons of gravitational force on Lisa by the Earth. Because initially we have what the action force is 500 newtons on Earth by Lisa, and if we're using the Newton's third law, we're going the other way around, so we're saying on Lisa by the Earth, pushing upwards. And that is the correct answer, which about only 8% of students actually got that correct. This was one of the worst questions in VCE Physics about ever. Cool. Tension. So when it comes to tension, the best way to answer these type of questions is to draw some sort of diagram. Usually you're given a diagram, but what you want to be including is the force diagram. You want to draw arrows in the direction the force is going, so you can actually better understand what is happening. So the most common type of questions you would get are one of these questions. So you have some box, let's say it's 2 kilograms, and you have some box over here that is 3 kilograms. It's connected like this, and you would often get asked something like, what is the tension in the rope? The way I like to do these questions is I find this, and I know a lot of students find this a bit confusing. So what you can do, you can rewrite, you can redraw this diagram like this. 2, 3. And so in this case, we know what we like to call the driving force is the force of gravity. And so we can kind of redraw this diagram horizontally like this. Kind of redraw it like this, force of gravity. It's the same scenario, it's just that now it's just drawn horizontally. So this helps you actually see what's happening. So we have what we call a driving force, which is the force of gravity, which would be 3 times 9.81. So if that's the driving force, what is the acceleration of the whole system? And when you are calculating the acceleration of the system as a whole, you want to think of mouse works. Yeah, you want to think of this system as one big system. So you want to think, if I were to simplify this, you would want to think of this like a 5 kilogram mass that is being pulled by Fg. Cool. And whatever that value is will be the acceleration of the whole system. Yeah, that will be the acceleration of the whole system. If you were to find the tension of the rope would be since this rope, keep losing my mouse. Since this rope is pulling this mass, the tension of the rope would be 2 times whatever the net acceleration of the system is. And yeah, whatever that is should be your tension. So just a quick reality check you can do with these types of questions is if the tension force is greater than the force of gravity or the driving force, you know you've done something wrong. Another reality check you can do is if the acceleration of the system itself is greater than 9.8, then again you've done something wrong and you want to double check your answer. So usually what happens is the acceleration of the system should be lower than 9.1 because you're pulling you're pulling more mass. So the overall acceleration will have to be lower than 9.8. And because of this, the actual force of tension, will also have to be lower than force of gravity. If you struggle with these types of questions, just have a few examples on your cheat sheet, and hopefully it'll make sense to you on the exam. Cool. Next thing we have is apparent weight. So when you're standing or anything, the weight that you feel is the normal force that is pushing up on you. So let's say this is you. The weight that you feel is this force, which is the normal force of the ground pushing up towards you. So if the normal force is greater than the force of gravity, what you've experienced the ground pushing up on you more than your weight force. And because of this, you will feel heavier than you actually are. Inversely, if the normal force is lower than the gravitational force, the ground is pushing up on you at a lower force than gravity itself. And because of this, you are going to feel a lot lighter than you actually are. And this brings us to weightlessness, which is when the normal force is equal to 0. Because it's equal to 0, you don't feel any weight because there's essentially nothing pushing up on you. This formula, if you remember your circular motion stuff, you have this formula V is equal to root GR, and that is the formula you use when you have no normal force. This is something that is not on your formula sheet. So yeah, this is something that should go on your cheat sheet, and a little label saying that this formula can only be used in this formula can only be used in circular motion when your normal force is 0. So just have that on your cheat sheet so you know when to use this. um, one of the most difficult questions that happens students struggle with when it comes to exam is springs, um, especially the spring systems when you have some weight that is being dropped from uh, some height. So the reason this is a bit confusing is because when it comes to springs, there are two different types of uh, ways you can look at springs. So the first way is looking at the energy. And when it comes to the energy, there's usually three types that we care about. First of all is the gravitational energy, which sometimes is written as the GPE, or gravitational potential energy. The second type is the spring energy, which is sometimes written as SPE, and the kinetic energy, which is the kinetic energy of some mass. And all of these have their own formula, and you should be pretty aware of those. The second way you can look at springs is by the force. So when it comes to dropping a spring from a certain height, there is two types of forces that's going to be acting on it. The weight force, which is just F equals mg, and the spring force, which is F is equal to kx, where k is your spring constant, which has its own units. The confusing part is which one of these do we use? Do we use the force or do we use the energy? And I'll explain which one you use in a bit. But just quickly, I want to go through energy first. Cool. Quickly going to go through energy. So you may have seen some table like this or something similar to this. So when we have that's not what I was meant to do. When we have a spring, so let's say this is our spring, let's say this is our mass. When it's at the highest position, just load the rest of it. Cool. When the mass is at its highest position, what is happening is that the gravitational energy is the maximum. The kinetic energy is 0 because the mass is not moving, and the spring energy is 0 because the spring is not extended. When we are at the bottom of our extension, so let's say this is our spring, this is our mass, at this position there is maximum extension. So all of the kinetic energy, all of the gravitational energy has been converted into extending the spring for as long as we can. So you can kind of imagine that here's the weight, we've dropped the weight, and it's accelerated all the way down to the bottom, where it's momentarily at rest, where the spring energy is going to be maximum. When you're at the middle, there is one quirk that you have to keep in mind. So when you're at the middle, the gravitational energy is going to be half because you're halfway, you've fallen like half of the distance. When it comes to the spring potential energy and the kinetic energy is going to be a quarter of the total energy, and the spring potential is going to be a quarter of the total energy. I'm going to do some algebra to show this, but it's not really worth the time. So I just have to trust that the kinetic energy is going to be a quarter, the spring energy is going to be a quarter, while the gravitational is going to be half of the total energy in the system. And the second type of way you can look at springs is by looking at the forces. So you can see that when it comes to the forces, the force of gravity is always constant. The reason being is because force of gravity is just equal to F is equal to mg, where mass is constant and the gravity is going to be constant. And because of this, the downward force of gravity is always going to be the same. When it comes to the force of the spring depends on K. not k, it depends on x, where x is the extension. So it makes sense that the more we extend the spring, the greater the force the spring has. And just quickly, when it comes to spring, the energy of a spring. So energy of a spring at the beginning. So this red line is our gravitational energy. At the beginning, the gravitation potential energy is going to be the greatest. As the weight drops, the gravitational potential energy is going to decrease at a linear rate. The reason it's linear is because GPE depends on height, and as height decreases, we know the GPE is going to decrease. When it comes to spring and kinetic energy, you have to keep in mind that because it is squared, so spring potential energy is distance squared while kinetic energy is velocity squared, it's going to give us a quadratic representation. When it comes to the spring potential energy, the spring potential is always increasing. The reason being is because as the spring increases, the displacement is also increasing, and because spring potential is dependent on displacement, the spring energy is going to increase all the way to its maximum. While the kinetic energy, it reaches its maximum at the midpoint when it starts decelerating all the way to zero, at which point we know the maximum energy is all contained within the spring. When it comes to the force graphs, this is what the force graph looks like. So we know the force of gravity, or the weight force, is always going to be constant because force is Fg, force is mg, where m is constant and g is constant, so force of the weight is going to be constant. The spring force is a linear relationship, kx, and we know this increases as displacement increases. And the net force is essentially force of gravity minus the force of the spring. It doesn't matter which way you do it. Depends which way you take as positive, which way you take as which way you take as negative. A net force is just subtracting the two forces, and we know at the center or the midpoint, these two forces are going to cancel out, and you're going to have zero net force. So this brings us to this question. In this question, we have a mass of 2 kilograms, spring constant of that much. We know the spring is being allowed to fall from its maximum height. So we want to calculate how far does the spring stretch until the mass comes to a rest. Cool. There is 2 ways you can do this question. You can either I'll show you the correct way to do this first. So the spring is being dropped from that height and it's being allowed to fall to allowed to fall down here. So what we can do, we can equate the 2 energies. So I can say that the initial gravitational energy, so gmh, is equal to the final mkx squared. So initially, the gravitational potential energy is maximum. At the bottom, the spring potential energy is maximum. So all of this gravitational has been converted into spring. And so to solve this, you would say, so the mass is 2 times 9.8 times the height, which we don't know, just call that x for now, is equal to half times 20 Newton meters. Just make sure that the units are correct. Sometimes you are given this unit this in kilo Newton meters. So just be aware that the units of this can change. 20 times x squared, because the distance we don't know, we're trying to figure that out. And solving for this, you get x is equal to 1.96 meters. Again, if I'm going too fast, just feel free to screenshot this question. Yeah, just feel free to screenshot, take a photo, whatever works for you. So as you can see, this question was not done very well. About 70% of students did not get this question correct. And the reason is because a lot of these students, they used forces. They used forces, which is not what you're meant to do. So what they did is they said mg is equal to kx, or in other words, the force of gravity is equal to the force of the spring, which is not correct. The reason we don't use this is because there's a difference when you can use this and when you can use this. In what I like to call a dynamic scenario, so in this case, the weight is just being allowed to drop, it's accelerating, it's moving, it's dynamic. Because it's dynamic, it's moving, we are allowed to use this. When you use the forces, when you equate the forces, that is when you have a static scenario. I think it's called static equilibrium in some cases, but in such a scenario, the mass itself is not allowed to move. So let's say we're holding onto the mass, we are just lowering it slightly until we meet the equilibrium. In that case, we would be using mg is equal to kx, because the mass is not being allowed to move. We're just keeping the mass still. Whereas this case, in this case, we are allowing the mass to fall freely, and because of that, because it's allowed to fall, it's gaining kinetic energy. Because of this, we want to be equating the energies. Cool. Circular motion. Hopefully that isn't too bad. You usually just use these two formulas. Acceleration is v squared on r, and acceleration is 4 pi squared r divided by t squared. Two things that you have to keep in mind. In a circular motion, the velocity of the object is always traveling at a tangent to the circle. And the second thing is that the net force is always towards the center. Cool. And yeah, the way you can calculate net force, because we know the acceleration, the net force is just, because we know force is just mass times acceleration. If this is our acceleration, then the force would just be these formulas times the mass. Cool. Another thing you have to keep in mind, because the direction is always changing, the velocity is always changing, because we know velocity is a scalar, so not scalar, it's a vector. It has a magnitude and a direction. And because the direction of the velocity is always changing, velocity is always changing. And because velocity is always changing, it is accelerating. And yeah, so we know acceleration is change in velocity divided by the time. Because there's a change in velocity, we have some sort of acceleration. But what you have to keep in mind, what I said before, is speed and velocity are once again not the same thing. In a circular motion question, what happens is the speed is constant, but the velocity is always changing. And because it's always changing, we say it is accelerating. So that is one thing you want to keep in mind. It's a very common multi-choice question when it asks you, you're given a scenario and it's asked like what is the speed and like what is the velocity. In such cases, you want to remember that speed, again, always constant, velocity, always changing. The next type of questions you get with circular motion are one of these. So the equations for these are different depending on the type of scenario that we have. So in this case, we have a car at the bottom, and the bottom here we have a car at the top, on top of the circle, And the other type of scenario is where you have a car that is over here and on top of the circle, but on the other side. In VCE, you will only be asked one of these three scenarios. The other ones, it's too difficult. It's beyond the scope of VCE, and these are the only three that you will be dealing with. The equations for these will be different depending on the scenario. So in this case, where the car is at the bottom, this is mv squared divided by r, or sorry, this is your net force. Net force is equal to force normal minus force of gravity. And the way you get these formulas from is as such. So we know the net force is always upwards. It's always towards the center. So we can say this is our net force. What is net force? Net force is essentially the summation. So net force is essentially the summation of all the forces. So in this case, there's two forces. So we know the net force is the force of gravity plus the force of the normal force. What we want to know is which direction are the forces acting. So let's just assume that upwards, in this case, upwards toward the center is positive. So if that's the case, we know this is force of normal, this is the force of gravity. If you assume upwards is positive, then we know the net force is equal to the positive force, normal force, plus the negative force of gravity. So applying the same sort of logic for this one, assuming that net force is downwards, and downwards is positive, we know this is downwards is force of gravity, we know this one's force of normal. We know the net force is therefore equal to the force of gravity plus the force, minus, let me just double check that, force of gravity minus the force of normal. And yeah, that's essentially where those formulas come from. Again, this is good, really good cheat sheet material. I highly suggest you have this there. Another way this formula is sometimes written is in terms of tension. So sometimes you'll get some string, some mass being spun around the string. And so these formulas can sometimes be written as net force is equal to force of gravity, but instead of having a normal force, you have a tension force. And yeah, same thing with this formula. So net force can also be written as force of normal minus the tangent force, minus tangent force. And yeah, you can apply the same thing to this scenario, and I'll leave that as an exercise for you. Cool, so this brings us to another VCAR question. So this question, I think, another 2021 question. So in this question, we have some roller coaster being dropped from some height, and it's going through a loop. The question is asking, considering the forces acting blah 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 blah, show that the force to just remain in contact at point C is given by this. So when a question says to just remain in contact, that is saying that the force, or the normal force, is equal to 0. And we want to calculate essentially how to calculate the normal force at this point. So at point C, we know the net force is equal to, since the car is going to be here, is equal to the force of gravity plus the normal force. The reason being, the reason we're adding both of them is because at this position, net force is downwards, so let's assume that is positive. We know the gravitational force is also downwards, and we know the normal force is always downwards. So if you were to sum up everything, the net force is just the gravitational plus the normal force. Cool. We can calculate the net force by using mv squared on r. So we know mv squared divided by r is equal to mg plus the mg plus, it's the force of gravity plus the force of normal. Since we know the normal force is equal to 0, since we know this is equal to 0, which we got from this information, we know mv squared divided by r is equal to the force of gravity, which is just mg. And solving for all of that, we get v squared divided by r is equal to g, which is what we wanted to show in the original show that question. So something along these lines, you'll get the 2 marks. Just to be sure, I would emphasize that you know that the normal force is equal to 0. That's where the other mark, I think, came from. Cool. Banked angle, essentially you're just using your trig to find out what the different forces are going to be. And so the best way to do this is to draw one of these diagrams. So as long as you get the information, you can plug them in, use your trig, and you can calculate whatever needs to be calculated. The key thing with banked, with questions like this where you have some bank track, is the net force is towards the center. So in this case, we have some car traveling around a banked velodrome or something like that, and in this case, the net force is always towards the right. The difference is, in the case of a inclined plane, where we have some box that is falling down, in this case, the net force is downwards in this direction. But in a circular motion sense, or in a banked angle sense, the net force is towards, parallel to the ground. But for banked angles, it is straight down. And these are the 2 things that you have to differentiate between, and making sure that you don't mix up the 2 scenarios. Cool. I think that's almost everything for Newtonian stuff. If you guys have any questions, put them in the chat and I'll try to answer them as soon as I can. Cool. The last type of circular motion that we have is circular motion with orbits. When it comes to orbital motion, there is only one force that is acting on a satellite, and that force is the weight force. So if you were to get asked to draw the force diagrams, the most common mistake that is made is they draw this perfectly fine. Velocity, velocity is always tangent. Force of gravity is obviously downwards. A lot of students, they would draw something like this. They would say force of gravity is downwards, the net force is downwards. They'll include some sort of normal force. That is not what you do. There's only one force that's acting on it, and it is the force of gravity downwards. And because of this, so satellites are essentially in a type of free fall where satellites are always just falling. But because of the circular motion, satellites don't actually fall to the ground. Oh, yeah, and this point is very important. Because the only force acting on a satellite is the weight force, there is no normal force acting on the satellite, which is why you can't just say this, and that would be wrong. Because there is no normal force, if you were on a satellite, you would feel weightless because there is nothing pushing up against you, and so because of this, your apparent weight will be 0. Cool. Which brings us to this formula. So since we know the only force acting on a satellite is the gravitational force, we can equate the circular motion part to the gravitational part. So this side is our gravitational. It comes from a gravitational field's formula, where force is equal to gm divided by r squared. And we can equate that to our circular motion formulas because we know force is equal to mv squared on r, or force is equal to 4 pi squared r cubed divided by t squared times the mass. And when we equate those two, we get this formula. You may have seen this before, where it is 4 pi squared r cubed is equal to gmt squared. And so this is the formula that you would be using for circular motion when it comes to orbital motion. It's a pretty big formula. It's very easy to mess up, especially with the big G, which is a really big number. It's like 6.67, 10 to the negative 20, negative something. If you don't know, look it up in your formula sheet and don't do what I did and memorize all of the constants, because you are guaranteed to get them wrong at some point. So yeah, the inputs to this formula is your radius. Keeping in mind that this is your orbital radius and not your altitude. Orbital radius and not your altitude. You really want to double check that you've not been given the altitude. If you have been given the altitude, you want to convert that into orbital radius by adding the radius of the Earth or radius of whatever the planet we are on. Additionally, this formula is not on your formula sheet. It's something that you have to derive from this. And because of this, this is excellent cheat sheet material. And also, I highly recommend that you have a transposed version of this, so you can isolate the radius or you can isolate the time. I'm not going to do it now, but this is a good exercise for you to just quickly transpose those two formulas, have it in terms of radius, have it in terms of time, and so you can have those two variations on your formula sheet just to help you when it comes to your exam, so you're not stressed in trying to rearrange this monstrosity. Cool, so we have this question. This is the perfect time where you would be using you would be using your orbital motion formula. So pi squared, 4 pi squared r cubed is equal to g mt squared. And the reason I picked this question is, as you can see, it is a 4 marker. Why? There's a lot of steps to this question. From the top of my head, I think you get 1 mark for using or having some mention or using this formula. The reason being is because, as I said before, this is a formula that is derived and it's not expected that you know this. So as long as you have some mention of this, that should be 1 mark. Cool. So the way you do this, 4 pi squared r cubed, 4 pi squared, the radius is, we don't know what the radius is. We don't know what the radius is. G times the mass, which is 5.98 times 10 to the 24, times the time, which is 86400, 86400 to squared. So you do this you would do this question, you rearrange everything, and you would solve for r. So let's say r. I don't have the answer with me. Oh wait, sorry. Yeah, r is equal to 4.23 times 10 to the 7 meters. And obviously you would do this properly without actually looking at the answers, like I am. But we're not done. Again, this is a 4 marker question. There is going to be a lot more than 2 steps. There's going to be at least 3 to 4 steps. So yeah, that is a good way you can recognize how hard a question is going to be by just looking at the marks. So if it's a 3 mark, 4 mark, you know that if you've just done 1 or 2 steps, you've definitely not done enough. The reason we've not done enough is because we are asked to show that the altitude of the geostationary satellite must be that much. Geostationary just means that the period of the satellite is the same as the period of the rotation of the planet. So in this case, the geostationary orbit, its period is exactly 1 day, and the time that it takes for the Earth to spin around itself is also 1 day. So this is a quick aside. If we want to find the altitude of the geostationary orbit, we know that the radius of the Earth is 6.37 times 10 to the 6. When you subtract that, you should get 3.59 times 10 to the 7 meters. And cool, and that should be your full 4 marks. Yeah, a bit of a lengthy question, but as long as you can do all of these, you can show this formula, show the substitution, show the rearranging, and most importantly, showing this part that you're subtracting the altitude, you should be able to get all 4 of those marks. Cool. The next topic. EMF and flux. Cool, EMF and flux. It's very easy to confuse the two, especially when the graphs of the two look really similar. What you have to keep in mind, flux is this. Flux is measured in WB, also known as Weber, I believe. Flux is essentially the area of a coil multiplied by B. Cool. So in this scenario, what is happening? So we have some coil. It's starting at 0 degrees. When we're rotating the coil, so we rotate it a quarter rotation, another rotation, another rotation, another rotation, and this is our flux graph. And so we can kind of make sense of it. So when it's at 0 degrees, the coil is perfectly flat. Since the coil is perfectly flat, the area that is perpendicular to the magnetic field is 0. Why? Because the coil and the magnet are traveling parallel to one another, so there's no perpendicular coils, no perpendicular magnetic field. However, when we are at 90 degrees, when the coil is upright, what is happening is that we actually have perpendicular magnetic field that is hitting this side of the coil. And because of this, we have flux. And at that position, because it's perfectly perpendicular, the flux is going to be maximum. And yeah, this cycle will repeat for 180, 270, and 360 degrees. The EMF graph, sometimes it gets a bit confusing because they are very similar. The EMF graph comes from this formula. Faraday's law, which is just number of coils times the change in flux divided by the change in time. So change in flux. Change in flux, you can sort of think of this as the derivative. If you've done methods, you know what I'm talking about. So this graph is kind of like a sine graph, and the derivative of a sine graph is like a cos graph, so you get something that looks like this. This makes sense. So the maximum EMF is generated when the change in flux is the greatest, and the greatest change in flux occurs at this. Wrong point. The greatest change in flux will occur at this point when the flux is 0. So you can see at these two maximum and minimas, the greatest flux will the greatest EMF will happen when the flux is equal to 0, and and you would generate 0 EMF when the flux itself is at its greatest. So at these 2 points. So these 2 points, we have the greatest flux. So our EMF is going to be the lowest because our change in flux is the lowest. Cool. So another type of graphs that we can get are one of these. So In this case, we have this and this, which is our one second. Oh yeah, which is our AC current and our DC, AC and DC currents. So this is our AC, no, sorry, not currents, AC and DC, so AC voltage and our AC current. So over here, if my pen works, yeah, so this is our AC voltage, this is our AC current. So to convert from AC to DC, or to convert from AC to our RMS, you would divide it by root 2. One thing you have to keep in mind, we are dividing by the peak voltage. The peak voltage is this distance from here to here. What you don't use, you will never use this peak to peak. No, peak to peak is useless. Questions always give you the peak to peak to trip you up, but peak to peak, about 100% of the time is pretty useless. You always want to be using the peak. So yeah, peak is just the distance from here to here. Divide that by root 2. That gives you your RMS, and that is the same as the current. Yeah, hopefully this is coming back to you. So this brings us to this question, which, as you can see below, only 15% got it. 15% of students actually got full marks, where about 85% of students did not get this question correct. So we have some coil, and we have described the orientation of the rotating field such that the magnitude of EMF is at its maximum. So we know EMF is the maximum when change in flux is the greatest. And this happens when and only when the flux is equal to 0. So for the flux to equal 0, the coil has to be, that's not how you spell coil. The coil is not what I was meant to do. Coil will have to be perfectly horizontal. And something along those lines, if you can say this in a proper sentence or a proper dot point, you'll be fine. So if I were to answer this question, I'll be including Faraday's law. I would be saying that EMF is maximum when the change in flux is greatest. You can make a reference to Faraday's law. I can say EMF is equal to N delta flux divided by time. And so EMF is greatest when the delta flux is the greatest, and this will only happen when flux is equal to 0. And going back to our graphs, we can see that graphically, we know that the greatest EMF is when the flux is equal to 0, both in the positive and negative direction. But since it doesn't ask for positive and negatives, doesn't really matter. And yeah, this applies to the rest of VCE physics. We don't really care if it's positive voltage or negative voltage. We just care about maximum and minimums. Cool. So Lenz's law. Lenz's law is admittedly one of the more confusing ones. And so Lenz's law, the definition of Lenz's law is that any current induced in a loop will be in such a direction that the magnetic field created will oppose the change in flux. It's a bit of a mouthful, but how can we actually make sense of this? So when it comes to Lenz's law, there are 3 things that you want to be doing. So first of all, you want to know what is the current, what is the flux. So current, what is the flux? The initial flux. Initial flux. We want to know what is the initial flux. So after something's happened, so let's say we're moving a magnet, moving a coil or something like that, we want to find out, is the flux going to increase or is the flux going to decrease? From this, we want to, so if we know if the flux is increasing or decreasing, from this we want to know in which way will the which way yeah, focus. Let me start this again. So first of all, we need to know if the flux is increasing or decreasing. If it's increasing, the system wants to oppose the change, so it wants to decrease. If the flux is decreasing, the system wants to oppose this change and it wants to increase. So for this to happen, we want to figure out which direction will the current go for it to oppose the change in flux. So for that to make sense, we can look at this diagram. So what is happening in this diagram is that initially this magnet is being dropped downwards. And because of this, we know the magnetic flux is going to increase. And the direction of this magnetic field is going in this direction. It's going in this direction because it's the south end. Since we know a magnet is like this, north and south, a magnet goes like this. So applying that same sort of logic to this magnet, the magnetic field is traveling in this direction upwards through the coil. And since the area of the magnet that is perpendicular to the coil is increasing, we know that the flux is going to increase. And because of this, the system wants to decrease the flux. For this to happen, the current has to travel in the clockwise direction. The reason it's clockwise is because if you use your right-hand thumb rule, what you're going to see is that the induced magnetic field from the coil is going to be in this direction. It's going to be drawn a different color. It's going to be in this direction, downwards. So we have this magnetic field going upwards, we have the induced magnetic field going downwards, and they're sort of going to cancel each other out. And this cancelling is what is opposing the change in flux. When you're in the middle, because the flux is always the same, there's no change in area that is perpendicular to the coil. Because of this, there's no change in flux, and because there's no change in flux, there is no induced current. And at the end, the current is going to travel in the opposite direction. So one second. Yeah, it's going to travel in the opposite direction because the system, once the magnet is falling down, the flux is changing, and we want the flux to increase. So it's the coil induced current is going to travel in the opposite direction. Cool. So this is another question. Hopefully we've done something similar to this before. So in this question, we have a coil with side lengths of this much. It has 10 turns with a uniform magnetic field of that much. The shaft makes 2 revolutions per second. Calculate the average voltage during 1/4 of the rotation. And you can see it's a 3-mark question, and about 60-70% of students did not get 4 marks for this. Okay, I'll go through this question and then we can see where the common mistake is. So we know the flux is equal to the area, which is 2 times 10 to the negative 3 times the area. And in this case, I'm assuming it is a square coil with sides of 0.4. So the area is going to be 0.04 squared because it is in centimeters. And this gives us a flux of 0.0. Yeah, 5 zeros. 1, 2, 3, 4. 0.0000032. Hope just double check that, make sure I haven't done that wrong. So this is our flux. So next thing, we want to calculate EMF. So EMF is equal to N times the change in flux divided by time. So we know the N, the number of turns, is equal to 10. We know the flux is 0.0000032, if I did that correctly. And we know change in time. So this is where a lot of the students made the mistake. So the first piece of information is that it completes 2 revolutions in 1 second. And so using our frequency formula, so frequency is equal to 1 divided by time. The other way around. Period is equal to 1 divided by frequency. Divided by frequency, and since the frequency is 2, the period of this graph is half a second. However, we're not done yet because the question is asking for 1/4 of a rotation. So if it takes 1 second for 1 rotation, for a 1/4 second, this is going to take a half divided by 4, which is 1/8 of a second. And so 1 divided by 8 gives us 0.125. So doing the math for this one gives us an average EMF of 0.0000256, assuming I typed that correctly. If not, that's basically how you would do these questions. So you really want to double check if they've given you if they've given you frequency, you want to convert that into period, and if they've given you anything sneaky like this, where they're asking for 1/4 rotation, something along those lines. Cool. So another thing, another topic that is not done very well is transmission lines. And so when it comes to transmission lines, the key formula that you want to keep in mind is power loss is equal to I squared on R. And there's a lot of questions, a lot of qualitative questions that ask you why do you want to increase the voltage of something? Because we know the power is equal to voltage times the current. If we increase the voltage, the current has to decrease, and if the current decreases, the power loss will decrease by a factor of current squared. And because of this, we want to be using step-up transformers so we can reduce power loss across a longer transmission. So these are the type of qualitative questions that you would get asked. So so in this question, sometimes people are concerned about high voltages, and they propose that the power could be transmitted at a lower voltage. The reason this is wrong is because at a lower voltage, the current is greater. If the current is greater, then the power loss, which is I squared on R, our I squared times R, is going to be greater. And so because of this, townspeople are wrong. The main issue with this question was, as you can see from the examiner report, is that a lot of the students just copied information from the A4 sheet and didn't link it back to the original question. So a lot of students, they would have said something along the lines of increasing the voltage will decrease the current, which increasing the voltage decreases the current, which decreases the power loss. That's perfectly fine, but the issue with that, it's not relating to the original question. The original question is talking about high voltages. The question is talking about the concern of high voltages. So you would say something along the lines of townspeople are wrong because greater the voltage, the greater the lower the voltage, the greater the current, and the greater the current, the greater the power loss. So you always want to be linking back to the original question. You can look at your cheat sheet for a guide, but you always want to link back to what the question is actually asking. So here's a quick calculation question. I know a lot of people struggle with transmission lines. So the way we'll do this question, I'll let you quickly read this in your own time. You can pause it if you feel free to pause it. So the way you do this is we want to calculate the power loss in the transmission. And we know power loss is equal to I squared R. Cool. We know the resistance. In this case, because it's two lines, each with 2 ohms of resistance, we want to be taking the total resistance, which is equal to 2 plus 2, which is just 4. Current we don't know. However, we've been given this piece of information where the globe has 2 volts with 4 watts of power. So to convert, we know P equals VI. So we know 4 is equal to 2 times current, and current is equal to 2. Cool. So we know the current of this section is 2 amps. But we want the current in the wires. So we are faced with this step down transformer. So in a step down transformer, what is happening is the current is going to be divided by a factor of 10, which gives us a half, 1/5 amps in the transmission line. So the power loss is going to be 1/5 squared times resistance, which is 4. Whatever that is will be your power loss. And the way you get, where I got this from, it comes from this formula. So N1 divided by N2 is equal to I2 divided by I1, which is on your formula sheet, just to help with, this is on your formula sheet, which is to do with these transmission lines. So in this case, we take N1 as 10, N2 as 1, is equal to is equal to current I1, cool. And solving for I1, the current 1 is equal to 2 divided by 10 amps. So the reason you do it in this way, so we know 1, 2, so 1 is our primary and 2 is our secondary. The primary is always on, it's always on like the left hand side, so the side where the power supply is coming from, you would want to use that as your primary. And for the secondary, you want to be using that as like the second thing. So in this case, 2 amps is kind of like our secondary current. You can do it the other way around, but just make sure that you keep things consistent. So the right hand side, if you want to use the right hand side as 1, all of the right hand side has to be N1 and I1, and the right hand side has to be I2, N2. So whichever way works, whichever way works for you, it's fine, as long as you keep things consistent. So if you have any questions, just put them in the chat below, and hopefully I can get back to you as soon as possible. Cool. Time dilation. One of the more confusing and one of the more abstract topics. So time dilation is given by this formula. T0 times lambda is equal to T, where this T is our dilated time, which is always longer. And T0 is our proper time, which is always our shorter time, being multiplied by lambda, and lambda is given by this, which is just 1 divided by 1 minus v squared divided by c squared. Cool. So proper time. The way you differentiate between proper time and dilated time. Proper time is the time measured in the same reference field as the events occur in space. So essentially, we want to see which person in the scenario is measuring the event from the same perspective, and that person would be our time, be the proper time. The dilated time is the person who is witnessing the event at a different reference field than the event is happening, and because of this, they are going to see the same event take a longer time. If it's a bit confusing, that's perfectly okay. The questions that get asked with relativity are fairly easy. They usually just tell you that this is the dilated, this is the proper time. So if it's a bit confusing, don't worry. The questions themselves are not. The questions themselves are pretty straightforward. Yeah, they're not as difficult as it is to understand these things, such as length contraction. So length contraction, same thing, but in the opposite direction. So length contraction is our proper length divided by our lambda. So in this case, our dilated time is always lower than the proper. Yeah, and L0 is just our proper length, which is measured in the same reference field as the object is. So the person who's at rest relative to the object is the person who has the proper length. Cool. And the last thing with, one more thing with this, length contraction is always in the same axis as the direction of travel. So let's say we're traveling in this direction. Length contraction will only happen in this direction, and it will not contract in the y-axis. Cool. The last thing with relativity is this thing about sort of dilated mass. It's given by this formula where your dilated mass or your relativistic mass is your rest mass, so the mass if you're stationary, times gamma, and gamma we have calculated before is just your 1 divided by 1 minus c squared on v squared, no, other way around, v squared on c squared. Cool. So what this tells us is as you get faster and faster and faster, your relativistic mass increases. So as speed increases, your mass increases. Cool. And because of this, you get... Oh, I missed something. Yeah, so your relativistic mass is always greater than your rest mass. The reason for this is because gamma, that is not gamma, this is gamma, is always greater than or equal to 1. Gamma is never less than 1. So because of this, the relativistic mass is always going to be bigger than your rest mass. And because of this, you get one of these graphs. So in this graph, what is happening is we have my pen works. Cool. In this graph, we have relativistic mass, and we have sort of our rest mass in terms of classical physics. So in terms of classical physics, what classical physics is saying is that no matter how fast we go, the mass is always going to be the same. When it comes to relativistic mass, the difference is the faster we get, the more your relativistic mass is, because your relativistic mass is dependent on your velocity. So when it comes to comparing the two, comparing relativistic to classical physics, as you approach infinity, or as you approach the speed of light, your relativistic mass approaches infinity. And because it's approaching infinity, your mass is really, really heavy, and we know force is equal to ma. So if your mass is close to infinity, and we're multiplying that by acceleration, you require an infinite amount of mass to accelerate. And because of this, you can never actually reach the speed of light. So any object that has mass will never be able to reach the speed of light. Reason being is because the mass of the object is going to approach infinity. And you would compare that. You get some questions where you compare relativistic mass to classical physics, and so you would say in the relativistic sense that the mass is going to increase to infinity, so you cannot reach the speed of light. But while classical physics predicts that your mass is always going to be constant, so you can always reach the speed of light, which we know is wrong. So this brings us to another VCEE question. I think this is the 2014 or the 2015 question. I'll let you quickly read this question. Feel free to pause. Here's just some setup. The important thing is that the speed is constant and it's very high. So if it's very high, that means we know relativity is in play. Cool. So this question. It's asking which of these correctly identifies the behavior of the two clocks. So what's happening is this person, Barry, has a clock on Earth, and this person, Anna, also has a clock in the spaceship. Relative to each other, both of these clocks are going to be vibrating at the same time. Because Barry has his own clock and Anna has her own clock. Because their respective clocks, let's call this clock 1 and then clock 2, their respective clocks are in the same reference field as the person who's looking at the clock. So Anna, who's looking at clock 2, is in the same reference field as clock 2. So the time, so let's say it takes 1 second, is going to always be 1 second. Barry, who's on Earth, who has clock 1, is in the same reference field as clock 1. Because of this, Barry's clock is also going to be ticking at 1 second, which is going to be the same as Anna because both of them are in the same reference field respective to their own clocks. Cool. So just a quick calculation question. Looking for time. Cool. We have some question. The spaceship is traveling at 0.7 times the speed of light. Explain in terms of relativity what happens to the width and the height of what happens to the width of the spaceship. So the width is always the same. Reason being is because we are traveling in this direction, and the length contraction is only going to happen in the y-axis. The x-axis. So the width has no effect and will not dilate or will not contract. The second question is asking if the spaceship, if the person on the spaceship measures the length to be 135 meters, what is the length when it is stationary? So when it's stationary, that should be keywords for L0. So we know the length is equal to L0 divided by lambda. We know the length is 135 is equal to L0 divided by lambda. A shortcut to calculate lambda is this. So we know lambda is equal to 1 minus v squared divided by c squared square rooted. Because we've been given velocity in terms of c, so we know velocity is 0.7 c, instead of converting this into meters per second and then subbing it back into this equation, we can shortcut this process. Shortcut this process by just doing this. 1 minus 0.7 squared divided by 1 squared, all square rooted. Because it's given in terms of c, the c's sort of cancel out. So you can think of this as 0.7c divided by c. C's would cancel out, so you're just left with 0.7. That should be squared. Yeah, so that's one way you can just shortcut these types of questions. Cool, so this brings us to Young's double slit experiment, and hopefully this is something that is a bit more recent. Yeah, so thing with Young's double slit experiment, when you're explaining these types of questions, you want to be including the keywords such as antinodal lines, nodal lines, your maximums, your minimums or minimas. You want to be saying words such as path difference, constructive interference, in phase, out of phase, nodal lines, antinodal lines, and all of these things. As long as you use the keywords for these, you would get a lot of the marks for the explanation types of questions. So the way double slit experiment works, as you know, it's alternating between antinodals, which is our bright lines, and nodal lines, which is our dark lines. Cool. Yes, just quickly, path difference. Path difference, I know it gets a bit confusing. Path difference is essentially, quite literally, what is the difference in the length. So this minus this. As some of the questions do get a bit confusing. I know a lot of students get confused, but in the most basic sense, it's literally just what is this length, subtract this length. That's all path difference is. And so the path difference, if the path difference is equal to a whole multiple times the wavelength, we're going to see constructive interference, or we're going to see a bright band. If the path difference is a half multiple of the wavelength, then we're going to see a dark band, also known as deconstructive interference, or our nodal lines, or nodal. This will be our this will be nodal, and this one will be antinodal. Cool. And yeah, so this is a setup you would usually see. At the center, you want to keep in mind the path difference is 0, because if we have two lights traveling from here to here and from here to here, the distance both of the lights have to travel is going to be the same. So if you would calculate the path difference, you would get 0. So you get something like 1 minus 1 is equal to 0. That is why center is going to be 0, and it's always going to be the brightest. As you move across, as you move across by wavelength, the brightness of the light is going to decrease, and by the time you get to here, the third wavelength, it's going to be not as bright as the center. Cool. So this question, bit of a wordy question. So essentially, what's happening in this, what's happening here, is they have set up a double slit experiment. They have taken out the double slit temporarily, and they mark where the bright spot is going to be. So if you were to imagine, if you were to take off this these double splits, you're going to see a bright spot in the middle. So over here, that's going to be the bright spot. If I were to put the double split back, the question is, will this spot, the center, will that spot be a bright band or a dark band? And this spot is going to be a bright band. The reason it's going to be a bright band is because we know this point is the center. And at the center, we know the path difference is equal to 0. And if the path difference is equal to 0, we know n is going to be a whole multiple of the wavelength. And so it's a whole multiple of wavelength. And because of this, we are going to expect constructive interference, or we're going to see a constructive interference, and we're going to see a antinodal spot. Yeah, so as long as you include such keywords such as constructive, antinodal, a whole wavelength, a whole multiple of a wavelength, bright bands, you should be pretty set with these. How are we doing with time? We'll quickly go through this question. Cool. So in this question, we want to calculate the path difference at point P. Point P, which is over here. So at point P, I think it tells us somewhere. The point P is the second bright spot. If it didn't tell you this information, you would have to count it from the diagram. So this spot, so if M is the center, this is the first, this is the second bright spot. So if we know it's the second bright spot, we know N is equal to 2. So we know the path difference would be 2 times the wavelength. Wavelength in this case is 420, which gives us a path difference of 840 Newton meters. Not Newton meters, nanometers. And since the answer is in nanometers, we don't have to change any units. Second question. They've done the same experiment, but they've found that point P is now a dark band. It's the second dark band. And we want to calculate the wavelength. So if it's the second dark band, we know N is equal to 2. We know path difference is equal to N minus a half times the wavelength. We know N is equal to 2. So PD is equal to 3 on 2 wavelengths. Let me just do it properly. We know PD is equal to 2 minus wavelength. 2 minus half times wavelength. Path difference. Path difference is the distance the light has to travel. So at point P, the distance the light has to travel from here to here and here to here is going to be the same. So in that case, we can use the path difference that we found in part A. So 840 nanometers is equal to 2 minus a half times wavelength. And solving for wavelength, whatever that wavelength is going to be, will be your final answer. Last thing with these sort of questions would be your fringe spacing. So going back to this diagram, each subsequent bright spot and each subsequent dark spot is going to be a full wavelength apart from one another. So when it comes to something else, fringe spacing. Fringe spacing is the distance between the bright spots and the dark spots. We can calculate this by using this formula, something you've probably done before and shouldn't be something that is completely new to you. So this is going to give you the distance between subsequent dark bands or bright bands. If you wanted to find the distance between, let's say, 2 bright bands or 3 bright bands, you would have to multiply this by n, which is the amount of bright bands or dark bands we are covering. Cool. So the last type of topic we have is photoelectric, and hopefully this is a bit more recent, it's a bit more fresh compared to a lot of the top term 1 stuff that we've done. So essentially how these work, we have a vacuated glass tube, which is a fancy word for a vacuum. We have vacuum, we have some light that's going to hit in this case we have a sodium plate, but this would usually just be any sort of metal. It hits the metal, the electrons are going to travel in this direction. It's going to travel in this direction, it's going to complete the circuit, and the light or whatever, it's going to create a current, the light will turn on, or whatever we have connected to this current, whatever we have connected to this circuit. In terms of positive and negative, The left-hand side, or the side where the light is going to hit, is called the cathode, which is negative. And the other side, to which the electrons are going to travel, is called the anode, which is going to be positive. For anyone who's doing chem, anode and cathode, positive and negatives, are not the same as the chemistry ones. So just make sure, if you're doing chemistry as well, not to confuse anode and cathode. Cool. When it comes to these sort of diagrams, hopefully you've done something similar in a recent SAC. When you have these type of diagrams where you have volt and photocurrent in the y-axis, you'll usually get asked questions such as, what happens if you change the current, what happens if you change the intensity, what happens if you change the work function, or if you change the frequency of the light. So if we were to change the current, if we were to change the intensity, let's say if intensity increases, we know intensity will only impact the current. So if we were to, say, increase the intensity, we would see the same graph, but the y-axis is going to be slightly higher. Y-axis is going to be slightly higher because of the increased intensity, which is going to increase the current. When it comes to these graphs, the x-intercept is volts, and it's given here. So in this case, we have negative 185 volts. So this tells us what the work function is. So this tells us the work function of this metal is 185 volts, or electron volts. So this is the minimum amount of energy that you need to actually emit photoelectrons. Oh, sorry. This is, yeah. Cool. Some just a quick revision with photoelectric stuff. Quick revision. So work function. Work function is the minimum energy that you require to emit an electron. Threshold frequency is the minimum frequency that you need to emit an electron. These two things are kind of like the same thing. So work function is a measure of energy, so it is in electron volts. Threshold frequency is a measure of frequency, which is in hertz. Work function is the minimum energy required to move an electron. The frequency is the frequency that you need, so the frequency you need to obtain this much energy. So in that sort of sense, these two things are kind of like the same thing. And since we know the energy of a light is equal to E is equal to HF, we can evaluate this equation. So work function, so this is our work function, F0 is our threshold frequency, and so if you want to find the energy of a threshold frequency, it is going to be your work function. And all of that just comes from this formula where E is equal to HF. The third type of formula that you have to remember is this one. EK max is HF minus work function. This comes from the fact that the energy of an electron is equal to the light energy. Rewrite that. Comes from the fact that the electron's energy is the electron of, so the electron's energy is the energy of the light minus the energy of the work function. And so combining all of that, we get HF minus our work function is equal to the kinetic energy max. Yeah, and this formula hc on lambda, it is just E equals hf, but since we know frequency is equal to c divided by c divided by lambda, you can just substitute this instead of frequency. And doing the same with this formula will give us the same thing. Cool, so just a little bit of theory. The way the photoelectric effect works, we have some light shining on a piece of metal. We want to change the intensity of the light. We want to change the frequency or the color of the light, and we want to see how it impacts both the current and impacts the energy of the electron. So some results with the photoelectric effect. So we found out with the photoelectric effect, there's something called a threshold frequency, which, as we know, is the minimum frequency to actually emit those photoelectrons. Any frequency above, so if your frequency is above the threshold frequency, if you increase the frequency of the light, it's going to increase the stopping voltage. And stopping voltage is just another word for EK max. Or in other words, stopping voltage is how much energy does the electron have. So the energy of the electron. Cool. Last thing we found out is changing the intensity of the light will only change the current, and photoelectrons are emitted instantaneously. So this is the perfect example of what should be on your cheat sheet. So this is theory. This stuff is never going to change. You will always get questions about this. You will always get questions about to compare the photoelectric effect and the effects of the wave model. And because of this, you can pretty much usually just copy paste whatever is on your cheat sheet. But obviously, you don't want to be copy pasting, you want to be actually answering the question. Yeah, so the differences between the actual observations and the wave model. So our actual observations show the existence of a threshold frequency. If my pen works. Yeah, existence of a threshold frequency, and any light below that frequency will not emit any photoelectrons. Whereas the wave model predicts the opposite. So the wave model says any frequency of light should be able to emit photoelectrons. It doesn't matter about the intensity or anything. Any frequency of light will, given enough time, should be able to emit photoelectrons. Any intensity. Second thing, the photoelectric effect shows any light above the threshold frequency. As you increase the frequency, will increase the stopping voltage or the energy of the electron, the EK max. According to the photoelectric effect, increasing the frequency will increase only the current. And the last two differences is that increasing the intensity increases the number of photoelectrons increased, which increases the current. Whereas the wave model predicts as we increase the intensity of the light, it's going to increase the kinetic energy of the photoelectrons, which we know is wrong. And last one is just that the wave model, not the wave model, the photoelectric effect shows photoelectrons are released immediately, but the wave model predicts that there's going to be some time delay. So as long as you can compare these two, you can talk about the observations and why the wave model fails or why the wave model is wrong by referring to the photoelectric effect and the observations of the photoelectric effect. You can show that show that light is a particle and not a wave. So again, this is really good cheat sheet material. So if you have something along the lines of this, some sort of table, you should be pretty set with these questions. Yeah, this is stuff that just went through. Yeah, so another simple table like this will just help you summarize everything. So yeah, so the photon model, so particle model, if we increase the frequency, increase the stopping voltage. In the wave model, it increases the current, but yeah, increases the current. If we change the intensity, it changes the number of photons emitted, which changes the current. But in the wave model, increasing intensity increases amplitude, which increases the energy of the light, which is incorrect. Yeah, so just quickly with EK max graphs, this is very similar to our y equals mx plus c graphs. Thing with these graphs is m, in this case the gradient, is equal to h, and since h is always constant, the gradients of all of these graphs are going to be the same. So in this case we have potassium and we have magnesium. Because the gradient is always h, the gradient is the same, so they're parallel. The y-intercept over here is the work function. So the amount of energy you need to eject an electron. And the work function will depend on the type of metal that we're using. So potassium has a lower work function than magnesium. Because of this, it also has a lower threshold frequency. So potassium, you would need a lower frequency of light to actually emit photoelectrons than compared to magnesium. So if we had a light with, say, 7 times 10 to the 14 hertz, it will only emit photoelectrons on the potassium and not the magnesium. And with these graphs, you can kind of just disregard all the negative stuff, because at these frequencies, there is going to be no photoelectrons emitted, and there's going to be no voltage created. Cool. The last thing we have is light versus matter. And we have the electron diffraction from the double or single slit experiment. So with this experiment, we found out that matter actually has a wavelength, and we call this the de Broglie wavelength. Hopefully you've done this quite recently, so it's pretty fresh. De Broglie wavelength is given by this. Wavelength is equal to h divided by p. When you are calculating wavelength using this formula, you always want to be using the 6.63 times 10 to the negative 34. Always. This is the one scenario where you cannot use the 4.14 version. So 4.14, do not use that version ever. So when you're calculating wavelength with this, always 6.63. The next thing that is important is if light and if a particle and a wave have the same wavelength, it means their momentums are the same, but momentum is same, but does not mean the energies are the same. Energy is not the same. Not same. Energy is not the same. The reason is because energy for light and energy for a mass is measured differently. So energy for light is E equals hf, while the energy for a mass is half mv squared. So just because the momentum is the same does not mean the energy will be the same. Yeah, so this is one of the questions where X by Y Roger is correct. So in this question, we have electron diffraction and we have an X-ray diffraction. and it produces a similarly spaced diffraction, which means the same wavelength, which means the same momentum. And these two students are arguing, will the energy of the X-ray have to be the same as the electron? And the answer to this will be no, because same momentum, same P, does not mean same energy. Cool. And to calculate this, I'll just quickly do it, just because of time. To calculate this, so we know the energy of the electron is QV. I'll do it in green. So for the electron, we know the energy is equal to QV, which is equal to 5,000, and this is equal to half mv squared. And we know the mass of the electron, so solving for velocity will give us 4.2 times 10 to the 7 meters per second. And a quick reality check, this value is less than the speed of light, so we've done something right. We haven't completely messed up this question. So now we have the velocity. We can use the velocity to calculate wavelength. So when a wavelength is equal to h divided by p, so this is the wavelength of matter. So wavelength is equal to h divided by mv. We just calculated the velocity. We know the mass, so subbing that all in, you get a wavelength of 4.74 times 10 to the negative 11. I'm just reading off the answers, but if you were to do this properly, obviously you'd be substituting your question values in. And in this case, h is always 6.63. Always 6.63. Cool. Now we know the wavelength. Question asks us to calculate the energy of the X-ray. So if we know the wavelength, then the energy is just simply hc divided by lambda. And yeah, I'm assuming they want this in electron volts, so you'll be using 4.14. It was a bit fast. If that was a bit fast, don't worry. I highly recommend that you take a photo. Just take a screenshot of this question and try attempt this at a time, and you should have got a final answer of 7.1 times 10 to the 4 electron volts. Cool. So just quickly, when it comes to actually doing the exam, sometimes you can run out of time. It's perfectly fine. Sometimes you don't time things correctly and you are struggling on time. If that's the case and you find yourself in that situation, I highly recommend that you at least attempt the final graphing question. The reason for this is because the final graphing question is the best bang for your buck. It's usually worth about 7 to 8 marks, and if you do this properly, can take you a maximum of 6 minutes if you do this correctly, and assuming that you don't mess up. So yeah, considering this from like a time perspective, this graphing question will always grant you the most marks for the time allocated. But that being said, you actually have to do this question correctly, and to actually maximize your marks for these types of question, you want to, one, have the correct scale. You want to write down the correct units. You want to be including error bars in X and Y direction. It depends from question to question. Sometimes they only want error bars in X, sometimes they only want error bars in Y. If there is going to be error bars, the question will tell you what the error bars are and will tell you how much error they want. And the final thing is you want to be using the entire graph paper. So let's say if I did this graph and my line looks like this, that is not very good because VCA want you to use the entire space. They want you to maximize the amount of space you use on the graph. So I would say as long as you use around 60% of the graph, you should be pretty fine. The final thing, when you're doing your line of best fit, make sure that it is actually the line of best fit. Some students, it's a very common mistake, they force their lines to go through the start and end points. So if I was doing this question, I'll show you not what to do. If I was doing this question, if I do a line something like this, and I force it to go through the final point, it's no longer a line of best fit. So a line of best fit, you want to have the same amount of points above the line and same amount of points below the line. You don't want to be forcing to go, you don't want to be forcing going through all of these points. And the last thing is for the gradient. If you're calculating the gradient of the line, use a large space. Use a large interval. And do not use the points. So let me just rub this out. So if you're trying to calculate the gradient of this line, do not use the points that they give you. You want to be using the points on the actual graph you draw. And you also want to be using a wide of an interval as possible. So you want to be picking something up here and you want to be picking something down here. You don't want to be picking 2 points that are close to one another. So like in this region, you want to be picking points that are as far apart as each other. Cool. So that's about everything for content-wise, but just a bit of just tips for the exam itself. Make sure you actually bring a scientific calculator. Don't do what I'm doing and bring a CAS, because you will not be allowed to sit the exam if you bring a CAS. So have a scientific calculator and know how to actually use the calculator. Make sure you understand the formulas, know what's on your formula sheet. There's a lot of constants. There's a lot of constants that are on the formula sheet. So if you don't know which constants are, just take a look so you know what information you can find on the formula sheet, because sometimes there's questions where they don't give you enough information, but you actually have to look in the formula sheet for those constants, and something like the mass of the Earth or the radius of the Earth. Sometimes you think you can't solve the question because they don't give you the information, but if you don't look in the formula sheet, you will never find, you'll never be able to solve that question. This is another important question. Important thing. Derived formulas. So formulas such as 4 pi squared r cubed is equal to gmt squared. These formulas that are not on your formula sheet should be on the cheat sheet. And finally, please make your own cheat sheet. Don't copy someone else's, because our cheat sheet is meant to be for you. It's meant to help you. It's meant to have content. It's meant to have dot points. It's meant to have things that is going to help you and not the person next to you. And also actually know what's going to be on your cheat sheet, and know what, just put worst case, just put everything, but you also want to know where all this information actually is. And finally, heaps of exam questions. Lots of exam questions. Past papers, past VCA papers, past NHT papers as well. I would say, from personal experience, I think minimum is at least 5 to 6. 5 to 6. That's how much you should be doing at least. But again, that is the minimum. You want to be doing as many papers as you can. The more the merrier. But the minimum, I would say, is at least 5 or 6, and that's not just for physics, but for all of your other subjects. Cheat sheet. Just one thing with cheat sheets. Cool. So these are some formulas that are not on the formula sheet. So if you want, you can take a screenshot of these, because these this is a quick reference of formulas that are not on your cheat sheet. And on top of that, I'm going to add this formula: 4 pi squared r cubed is equal to gmt squared. So if you want, take a screenshot of these formulas, because these are the formulas that are not going to be on your formula sheet. Cool. And just finally, just finally, the most important thing is trust that you know the content. You've been doing physics for about 2 or 3 years now, and this is when it's going to pay off. So trust that you know the content. You've been doing this for a year, so you know the content, and you just have to trust yourself that you know the content. And just some standard housekeeping stuff, making sure that you actually get a good night's sleep. I would highly recommend not to do physics the day before your exam. I would say don't do any heavy revision. Just look through your notes, look through your exam papers. Don't do any sort of heavy work. You want to leave that for the day after. And that's a tip I would keep for all of your exams. Don't do any heavy revision the day before. Just keep your revision really light day before. Just look through your content, look through your notes, look through past papers. And just finally, during the exam, making sure that you actually using your reading time, making sure that you find questions that are going to be time consuming. You can find questions that are going to be hard. If they're hard, skip it, come back to it. Physics is a long exam. It's 2.5 hours. Because it's 2.5 hours, the way physics is structured, it's not very time pressured as, say, methods. But because it's not time pressured, you can sort of take your time with these questions, because a lot of the physics questions are time savers. A lot of questions are 2-3 marks. It won't take you too long, and these questions will save you a lot of time. And as long as you can get those time-saving questions out of the way, it gives you a lot of time to tackle those harder questions. And so that is pretty much everything for today. Hopefully you found this lecture useful. Hopefully you learned a few things, and hopefully you are one step closer to finishing your revision, starting those exam papers. I highly recommend starting as soon as possible. Like I said, no more exam papers you can get done, the merrier. Again, not just for physics, but also for all of your other subjects. So with that, good luck for exams. I know it's a month away. It feels like a real long time, but I can promise you that month is going to fly by. And after you're done with the exams, you are free forever and never have to do physics ever again. So that is pretty much everything from me. So finally, just good luck, do your best, and trust that you know the content.